using Theta. I'll first of all outline the hardware, give a system overview, the file system, and so on, and move on to describing the software, programming environment, and how to build your code. And then, as Chris said, I'll describe how to queue and run jobs, and finish with some troubleshooting tips. So first of all, the hardware looks like this. Theta is a Cray XC40 system with an Aries interconnect in the Dragonfly configuration. There's nearly 4,400 nodes with more than 280,000 cores and a total peak performance of 11.69 petaflops. The system is put together as shown in the image from the cards to the compute blades and packaged into the cabinets. As shown, there's a 10 petabyte file system that I'll say more about in a minute. But for more details, please see the link at the bottom. The Theta node itself is a Xeon 5 7230 or Knight's Landing. And the key thing is on Theta, there are 64 cores per node, giving a total of 2.1 teraflops per node. Now, each core has 2 vector processor units, or VPUs, running AVX 512. So the vectors are 512 bits wide, or 8 double precision numbers. Each core supports 1, 2, or 4 threads in hardware. The on-package memory is 16 gigabytes of the high bandwidth or MCD RAM operating at 450 gigabits per second. Outside of that is 192 gigs of DDR4. There's also a solid state drive or SSD of 128 gigs. For file systems, home directories are located in the GPFS file system, Mira-home, with a default quota of 100 gigs. We encourage you to keep your major software and results data and so on in your home directories, but run your major calculations in the project directories on the Lustre file system, which includes the Eagle and Grand file systems at those paths shown. The default quota is 1 terabyte, but please feel free to request increases. So while the project directories data is persistent, it's not backed up, unlike the home directories, which are backed up. For more information, see the link at the bottom. Moving on to the software, the login nodes run Cray's full Cray Linux environment operating system, or CLE. And the key thing is that the compute nodes run a stripped down version called Compute Node Linux, which is not the same as what's on the login nodes. Now, on the login nodes, the programming environment includes support for languages such as C, C++, Python, Fortran, support for programming models, distributed memory and shared memory. So you'll find MPI, OpenMP, and OpenACC, as well as some PGAS models. The compilers include Cray, GNU, third parties such as Portland Group. Tools include debuggers such as DDT, performance analysis tools such as CrayPat, and so on. And the optimized libraries, BLAS, LAPACK, ScalaPack, PETSI, and so on are also there. For more details, this is just a brief overview, but for more details, see the link at the bottom that Chris also introduced earlier. And just briefly, how to log into Theta. This will come up again, but it's here just for completeness. Please SSH space your username at theta.alcf.anl.gov. And when you press return, press the button on your crypto card and enter your 4-digit PIN, followed by the sequence in the crypto card window. And remember that it's uppercase. Now, to build your code once you're on the machine, please use the compiler wrappers with these short names: lowercase cc for C, uppercase cc for C++, and FTN for Fortran. That is, do not use wrappers you might be more familiar with that start with MPI, such as MPI CC, MPI F90, and so on. Those Wrappers do not generate code for the compute nodes, whereas the shorter named ones do. Now, to switch between the compilers I mentioned, please use the module commands load and unload with arguments, examples of which are shown here. PRG env-intel is the default. You can also use Cray and GNU as described. Please see the link at the bottom for more details on that. Just a brief note about performance profiling debugging tools. All the non-system libraries and stuff is in /soft. There you'll find debuggers such as DDT in soft debuggers. Please see the link for more information. Performance tools such as Tau and HPC toolkit are in soft perf tools. More information at the link there. And then you'll see the installed compilers in soft compilers, applications in soft applications, and so on. Okay. Moving on to queuing and running jobs. On Theta, it helps to know that the job scheduler is called Cobalt and executables are invoked from within a script, as in this example. QSub, the Cobalt command, takes as the following arguments as examples: $A for the project name to which the compute time will be billed. In this case, there's a workshop project name. -Q for the queue, -T for the time in minutes, unless you use the hours, minutes, seconds format, -n for the number of nodes, and then the script. Please make sure the script is executable. You can skip the -Q command and QSub will send the job to the default queue. More about that in a moment. To see, please see the script, the link for more information. Now, within the script jobs, jobs are launched using Cray's aprun command. And this is what happens on the compute nodes. So aprun options followed by the executable and then its arguments. Among the options are n for the total number of MPI ranks, N for the ranks per node. And then if you have threading, j for the number of threads per core, d for threads per rank. And in this context, you may see the word hyperthread used a lot. Hyperthreads are similar to regular threads, just with some more features. The rank and thread placement or affinity is controlled using -cc, excuse me. And the most common argument is depth. There's a couple of other choices you can make, which are you can find out more about in the link at the bottom. Executables may need environment variables, which you can pass using --env. And an example of putting all that together is here. So the job script might look like this. There's the aprun command with the number of MPI ranks, the ranks per node, and then the threading is described with D and J, and the affinity depth. And the binary here would be an OpenMP binary, so it needs the environment variable OMP num threads. So in this case, you want the num threads equals 4 to line up with the -D4. So the binary needs OMP num threads and aprun needs -D. And then the rank and ranks per node should line up with the number of nodes requested from Cobalt. And in this example, you'll see that the QSub options are specified in the script using the #Cobalt syntax shown, in which case you can just type QSub and then the name of the script. For more information on bundling multiple jobs concurrently, simultaneously, or using workflow tools, please see the link at the bottom. Now, the production queues have the following policy. There's a single queue for the entire system, I mentioned, called just simply default. And priority is given to jobs using at least 20% of Theta. That's 802 nodes or more to encourage capability usage. A global limit of 10 jobs running per user, 20 jobs in the queue per user, minimum time of 30 minutes, and a minimum number of 8 nodes. See the link for more information. More on the policy. The wall clock times are a stepwise function to encourage scaling. So if you have down to 8 nodes, there's a maximum of 2 hours, 16 nodes, 4 hours, 128 nodes, 6 hours, and so on. Please see the link for a summary of that and more information. There's also 2 debugging queues with 16 nodes dedicated to them. These queues are named after the memory modes, which you can find out more about at the link shown. The memory modes are cache quad and flat quad. Cache quad is the more common that people typically use. There's a limit of 1 hour wall clock time, and in the debug queues, 1 job per user and a maximum of 8 nodes. See the link for more information. Now, Cobalt will create up to 3 files for a job. And the first file is a log of your QSub command and your run choices in aprun and environment variables and so on. And that's a file called .cobalt log with a prefix I'll say more about in a moment. And that's created when the job is first submitted. Now, when the job runs, there's 2 more files created reflecting the output from the user application to the standard error and output channels, so .error and .output respectively. Now, the prefix by default is the 6-digit job ID created by Cobalt, but you can also customize your job name with the -O argument to QSub. You can also append or add the job ID to that name if you so wish, as shown. Now, more commands for managing your job. If you wish the output from one job to be the input to another, then you can chain your jobs using the -- dependencies argument to QSub, as shown with the job IDs in a list. QStat is a command for giving information about the queues. Uppercase Q shows the available queues. Lowercase u, the information on the jobs for a specific user. Job ID will give the status on a particular job, and -FL will give a more detailed information. Please see the man pages for more information on QStats options. Other useful commands include node list for checking the available nodes, and also showres will show you the current, the scheduled reservations that might be on the system, might be running. More about that in a moment. More commands for managing your job. Qdel will delete a job from the queue. Qalter can alter the parameters of a queued job, as shown, except for moving the job between queues itself, which is done using qmove, as shown. To place a job on hold, type qhold, and to qrls releases the job. You can run an interactive job using the -I for to QSub, as shown there in that example. And when you type return, just wait for the shell prompt to appear, which may take a few moments. And then once you're in at the shell prompt, you can run jobs as you would in the script by typing the aprun command of your choice, as in the example shown. When you're finished, just exit the shell, or if it times out, the shell will end automatically. A note about reservations I mentioned. Reservations allow exclusive use of a set of nodes for a specific group of users and a specific time. Projects may desire a reservation to meet a sort of a hard deadline, perhaps a conference paper or something like that, but also to obtain, they're useful to obtain performance data, because the reservation prevents other users' jobs from running on that partition of the machine. A common use for reservations is the regular scheduled system maintenance or possible debugging sessions. So if you type showres and you see uppercase R.PM, the PM stands for preventative maintenance. If you see .HW or .SW, then hardware or software issues may be being fixed. During those reservations, the machine will appear idle. To see more about reservations, there's a link there, and email support for your any reservation requests you may have. Finally, if you do have problems and failures running jobs, we encourage you to examine core files using Cray's Abnormal Termination Processing Tool, or ATP, which you can set up with the environment variable ATP_enabled = 1 in your job script before the aprun command. On failure, a file will be generated with that name that you can view with the stat view command. Please load module load stat to access that tool. In general, we encourage you to retain all information about a job if it fails, including the ID, a copy or location of the 3 Cobalt files, and the exact error message. Please contact us, as Chris said, with any inquiries you may have. Email support at alcf.anl.gov, or call the help desk Monday to Friday, 9 to 5 Central, at the number there. There's a toll-free number as well. And, with that,